Hello again. Thanks for watching this video and studying your math with me. Remember to read your book. There are different examples there than on this video, and use the tools to make sure that you understand the material we cover on the video. Today's topic is called Systems of Inequalities and Linear Programming. Anytime we draw a line, it divides a plane into three sets of points. The points on the line itself and the points belonging to the two regions determined by the line. Each of those two regions is a half plane. So here R is the line, there's a half plane called P, the points up here, and a half plane called Q, the points down there. Line R is called the boundary of each half plane. A linear inequality in two variables looks like this. Here you see it is less than or equal to, it could be greater than or equal to, or less than or greater than. The graph of a linear inequality is a half plane, and perhaps the boundary is included. If there is not an equal sign, it is called a strict inequality and does not include the boundary. We indicate this with a dashed boundary, as we will see later. If you allow equal, this is called a non-strict inequality and does include the boundary, and that will make it a solid line, as we'll see in some examples soon. To graph an inequality in two variables, then we will determine the boundary, whether it's dotted or solid, and then we will look at determining the half plane. There are two ways to do it. One way is if you put it in the y-intercept form described here, and the other way to solve it is if you use a test point here. Here's the first example. Pause the video and let's see how you did. Let's see how you did. So the line should be included. Those are the intercepts, and when you do the test point or the y-intercept method, this is the shaded area. Let's look at another example. Note this one does not have an equal sign here. Let's see how you do. Again, we see that 0, 0 does satisfy the inequality, and the boundary is dotted, and that is what you should have, and those are the intercepts to help you make sure that you drew the correct line. Sometimes we have more than one inequality, particularly in linear programming we will have more than one inequality. So the solution set of a system of inequalities is the intersection of the solution sets of all the inequalities in the system. We will find this intersection by graphing the solution sets for all of them and seeing where they overlap and shading the region that was common to all the graphs. Here are two examples. Pause the video, do each of these, and let's see how you do. Let's see how you did. Here it should be this dotted region. These points, these are the approximations for those points, and these are the actual coordinates of those points of intersection. And the answer to this is this region. It is dotted on the boundary, but it is all of this. The second one, we end up with a blue region, a pink region, and a green region. But since this is a dotted line, that point is a circle. It is not included, and when you think about this, you see that these don't intersect at all one with another. So there is a null intersection there. And now we're going to talk about solving a linear programming problem using these ideas. First of all, we have to identify what are the constraints that we have in the problem. There always are constraints. We have to say what is our objective in the problem. We draw the graph of the constraints, and that forms a region of feasible solutions. We find solving simultaneous equations, the vertices, the corner points, and we see what value do each of these corner points have with the objective function. And the solution is a vertex that produces an optimal, either a max or min for the objective function. And we know from this theorem that if an optimal value exists, then it occurs at a vertex. Here's a problem. Please pause the video, read it, and give it a go. We'll look at a solution in a moment. Let's see how you did. If you let X be the number of MP3 devices and Y be the number of DVD devices, your objective is to maximize the profit P equals 30X plus 70Y subject to. We cannot make negative values of these devices. Y has to be less than or equal to 0, X has to be between 10 and 50, and Y must be bigger than or equal to X. So we graph all of those and we find the feasible region is the one I'm outlining now. It goes from that point up to here, over to that point, down to this point, and then down along this line to that point. So the corner points, 4 of them, are the ones we have to evaluate. We plug each of those coordinates into the objective function. We're trying to maximize it, and we see that the maximum value of the objective function is achieved at 5700 when these values of X and Y are used. Sometimes we also will do minimization problems. Here's an example of that. Please pause the video, read this, graph it, and try to solve it. And I'll return in a moment and we'll see how you do. Let's see how you did. When we let X be the number of capsules, Y be the number of chewables, the objective is to minimize the cost, which is 0.2X plus 0.1Y, subject to we must have a positive number of capsules or chewables, and so that's X bigger than or equal to 0, Y bigger than or equal to 0. And we also have these constraints stemming from the words. We draw the graph and we find that this is the feasible region. It's the region that is to the right of the boundary I am outlining. So that is having corner points as we indicate here. You can see what each one of those corner points is, and we shove those 4 corner points into the cost function. Now we're trying to minimize, and so it is 0.6 achieved by X being 1 and Y being 4. So remember, time is precious. Each day must count. Do the math. It will make you strong. I will see you in class.